So I'm now going to give you a lecture on probability revision, and the reason for that is because this is quite useful when we start talking about classification using likelihood functions and other issues in machine learning. So Venn diagrams can be a useful way to represent relationships between events. So an event is something which happens, and if A can happen or B can happen and they're mutually exclusive, what it means is we have discrete events with no overlap in a Venn diagram. So A and B here represent two events which are independent. Normally the area of the drawing as well, or the diagram, also could relate to the probability as well of an event happening. Now sometimes events are not independent and we get some kind of interaction between them, and that's represented by an overlap. So that's the intersection shown on a Venn diagram, and you can see that for C and D. So if you've got two mutually exclusive events, so either A can happen or B can happen, but they can never happen at the same time, the probability of A or B happening is going to just be the probability of A happening plus the probability of B happening. Right? So it's just going to be the sum of the probabilities. And we'd represent that on a Venn diagram in terms of events which don't overlap. Right? They're not overlapping, there's no intersection between these events. That's not always the case, right? So there's not always zero intersection, which is the case here. Sometimes we do get events which can overlap, so something can happen at the same time as something else happening. And then we'd represent it by the intersection A intersects B on this diagram, and related to the area would be the relation would be the probability that this actually happens. So let's now think about A or B happening when there's an intersection. And we said before, basically the area relates to the probability of the overall event happening. And when A and B are separate, then it's just the area of A plus the area of B that represent the probability of A or B happening. But now we've got an intersection, so we can't just say it's now related to the area of A plus the area of B, because what happens is the intersection appears twice in that calculation. So this intersection here, we have to account for the fact that if we say look at the area of A and the area of B, then we've got twice this intersection coming in, so we have to take it off in order to do the calculation. Thus, probability of A or B happening in this case, where we've got an intersection, is the probability of A, which relates to the area of A, plus the probability of B relating to the area of B, take away probability of the intersection of A and B, which is the bit in between, which would otherwise get represented twice in the calculation. Right, so we have to take that off. As a simple example of that is, I could ask the question as, what is the probability of picking an ace or a diamond? Right. So the probability of picking an ace, let's assume that we're randomly sampling from a card, so it's a uniform distribution. Therefore, the probability of picking an ace would be related to one of these four cards, 1, 2, 3, 4, out of 52. So we'd say the probability of that was going to be 4 over 52. What's the probability of picking a diamond? And that would mean it's one of these at the bottom here in this line. So basically there's 13 cards, so probability of that happening is going to be 13 over 52 if it was a random event. But we see also we've got the ace in there twice again. We've got an intersection between these things. Therefore, the probability of an ace or a diamond is going to relate to the probability of an ace, right, which is all of this lot down here, probability plus the probability of a diamond, take away probability of an ace and a diamond at the same time, because otherwise we've got that in there twice. So all we have to do now is just go through and say, what are the probability of these things? What's the probability of picking a card which has an ace and a diamond? Well, that's only one card, isn't it? That's just this one here. So 1 out of 52. So assuming it's a uniform distribution, that's chances of that happening are 1 over 52. Probability of ace, there's going to be 4 of them out of 52, so that's easy to calculate. Probability of diamond, 13 over 52. So the overall calculation is going to be taking out the divided by 52, it's going to be 4 plus 13, take away 1 over 52 as the overall probability that we have an ace or a diamond. So let's think about now some rule for probability, and we're going to lead in here to something called marginalization, which is how to get rid of one of the variables in a probability distribution by adding up or integrating it out. So let's first of all look at this, and we can see that the area of A represents to its probability, and that's going to be the blue area. And what we also see was we've got this event B, which has got 7 particular discrete states to it. In fact, you could consider it to be 7 discrete events. So we've got these 7 regions, but they all, well, some of them overlap with A. So, for example, something happening, the joint probability of A and B6, that's going to be related to this area here, right? And so on. So the total overlap between an A and B is just made by summing up all of these bits which are blue. So it's going to be this bit here plus this bit here plus this bit here plus this bit here, and that's what I've written down there. And that will be the probability of A happening. So basically what we want to do is we want to say, well, the probability of A is given by all of these individual joint probabilities summed up across all of B. So just like we just wrote before, what we need to do is we could write down the probability of each joint probability. So the probability of A given B6, A and B5, A and B3, A and B1. And what we do is just add all of those together. So for all values of B, we add all these joint values together, and that will give us the probability of A. And that's what we've written in this sum for the discrete case. What we do is we look at the joint probabilities of A and B, and we sum up for all B's, and then we end up with basically just the probability of A. Right? That's what it's saying. And if we had a continuous system, this is discrete, we wouldn't be summing up, we'd be integrating across all B's instead. And this process is known as marginalization. Let's think of a nice simple example with a probability table when we've got discrete values. In this table we represent the joint probabilities of x and y. So the x and y equals 0, x equals 0, y equals 0 is represented by that table entry, which is giving a probability of 0.2. Similarly, if we want when does the probability of x equals 2 and y equals 0, so what value is that? It's going to be 0.1. When is x equal 0 and y equals 2? Well, it happens with probability 0.2. And when is x equals 2 and y equals 2? That happens with 0.1 probability. So what we can do now, let's say we've got this table and I only care about the probability of x being something. How do I deal with this? Well, all I have to do, we just have to sum up all the probabilities, the joint probabilities in x across all possible values of y. So just like we were doing with that previous example, all we have to do is we just calculate for all of the y values, what's the joint probability, and we just add them all together and we'll end up with just the probability of x. So in other words, the probability of x equals 0 is basically, because these events are mutually exclusive, it's going to correspond to this value here, 0.2 plus 0.1 plus 0.2, and that will give us then, it's got rid of the fact that y can be something different. It's just saying across all the values that y can occur at, we just add up these probabilities, and that will give us the probability that x equals 0, or probability that x equals 1. We just add up all the ones in this row, right? Or x equals 2, we add them up in that row. So, important result here, another important result is that if we have two independent events, and then the probability of A and B happening is the probability of A multiplied by the probability of B. So in other words, if I have a dice and I throw it, what's the probability of getting a 6, let's say. Well, it'll be 1 over 6, wouldn't it, if it's a fair dice. So what's the probability of getting a 6 twice? Well, it will be a 6 multiplied by a sixth, because these events would be independent, right? So in that case, we can say probability of A and B happening is just the product of A and with the product of the probability of A with the product of probability of B. So this is called various things, including the basically the product rule when it's independent. Generally speaking, things aren't independent, right? In the general case, in which case probability of A and B happening is always captured by this expression, which is saying the probability of A and B happening is given by the probability of A multiplied by the probability of B conditioned on A, or the probability of B given A. That's another way of expressing that. And because this is a symmetrical effect, basically the probability of A or B, we can just swap the A's and the B's round. So probability of A and B happening is also the probability of B multiplied by the probability of A, given that B has happened. We can equate those two equations now and actually end up with Bayes' rule. So first of all, we obviously these are both equal to probability of A and B happening. So this part here on the right is equal to this part here on the right. That's what we've written here. And then we just divide both sides, in this case, by the probability of B. And this gives us Bayes' rule. Probability of A given B is the probability of A multiplied by the probability of B given A divided by the probability of B. And that's a very, very important result. We can think of that in terms of hypotheses and data as well. If imagine you've got some data. Let's say you want to do a classification. Let's say it was a set of apples or oranges. Classify as is it an apple, is it an orange? The data would be, let's say, pictures of the fruit. Is it picture of either an apple or an orange? And the hypothesis would be, what's the probability given the data? Is this, basically I want to know what the fruit is. I want to know what the probability that this is, let's say, an apple, or the probability that this is an orange. So this could be the probability of this thing be an apple given the data. And basically what this is what you want to do, right? You want to know what the probability of this thing is, let's say an apple. And what you do is you can use Bayes' rule to rewrite probability of hypothesis given the data as probability of the data given the hypothesis multiplied by the probability of the hypothesis divided by the probability of the data. And all we've done here, the A and B, we've just substituted in hypothesis and data into Bayes' rule that we had on the other page. So just to explain what these terms are actually known as, the probability of the hypothesis, right? This is like, this is your belief what the hypothesis would be. Let's say you had 100 apples and 1 orange. Then your hypothesis would be, if you didn't know anything about the picture of what you're being shown, if there's 100 apples and just 1 orange, and you kind of knew that, then probability that it's going to be an apple would be 100 divided by 100. Would be 100 divided by 101, because most of the time, that's what you'd expect, but you don't actually know because you haven't got the data. Now that would be your prior belief. Or if you throw a dice, your hypothesis that it's going to be a sixth that shows up would be 1 over 6, right? Because it's got 6 faces. Or the probability of it showing a 1 would also be 1 over 6, because that's if it's a fair dice, and that would be the default value. So, probability of data is just your prior belief in the data. Probability of data given the hypothesis is the probability of observing data. What is that probability of that data going to be given that we've got the hypothesis? And probability of the hypothesis is given the data, right? That's called the posterior probability of the hypothesis after we've also got the data. So we've got it, like I said, if you look at all these apples and you haven't seen anything, and there's 100 apples and 1 orange, then your belief would be that it's going to be an apple with probability 100 divided by 101, because that's the best you can do. But if you actually see a picture of what's going on as well, Then you've got the data given the hypothesis. You can then say something about what your improved estimate is, which is going to be your posterior probability. So this term at the bottom is something that we've got to think a little bit about. What's the probability of the data? In actual fact, most of the time we just ignore it in classification because it always happens, and it happens across all conditions, and you can just cancel it out. But let's think we couldn't do that, and what would we do about that? Well, if we've got, let's say, two classes A and B, and they're mutually exclusive, so the probability of data can also, if these are two mutually exclusive events, then the probability of the data would also equal the probability of the data and event A plus probability of data and event B, right? If A and B are mutually exclusive. We add these two together, we've marginalised out, in this case, what this thing, or the class this represents, to get the probability of the data. And this is what the term that we want at the bottom of our expression. That's why we're going this way. How do we get that? Well, we can then write probability of data given A as the probability of A given the probability of data given A, right? That's our product rule. And we do the same for the expression for probability of data and B, this joint distribution. That's probability of B given the probability of data given B. We can then substitute these two terms into the top term for probability of data, like so. So we've got our Bayes rule. Again, this is just doing it again. What it's just basically saying is we want to represent P of X in such a way that it's in the same form as the terms that we actually have in terms of X given A and P of A. So what we do is just like we did then, we just basically want to represent probability of X as the probability of X given X and A plus probability of X and B, where A and B are mutually exclusive. That's what we just did. We substitute those in, and then what we do is this is just exactly what we did on the other page, but we call it the A and B here. We substitute in the probability of X into the expression at the top, and then we've got our final expression for A given X in terms of X given A and PA, and also this other term at the bottom, which is also basically just sum of this for one event and also for the other.